Okay, maybe I will just recall a few things from the last lecture. Just the notation Tn was the n regular tree.
È segnato qua, non ti disturba. Io non ti disturbo.
P was an abelian group with no torsion. And then I give you the definition of an exchange pattern. M is a family of monomials MIT, I from 1 to n and t is a vertex of the 3Tn, where MIT is a monomial with a coefficient pjt, which is an element of p, and then this exponents for the variables. So this is an element in ZP polynomial in n variables with coefficient in the group ring ZP, but the coefficients are required to be in P. And then we have the four axioms. We have them here. First axiom, xj does not appear in njt for all j of t. Then axiom 2 is that if I have an edge t prime labeled by j, then xi divides njt implies xj does not divide n. This is x, yes, x. Does not divide njt. Prime. But these the two monomials njt and njt prime are relatively prime. Then axiom 3, I have 3 vertices. So the number of the axiom is related to the number of vertices involved. So this is t prime, t double prime, label I and j. And we have that xj divides mit if and only if xi divides nj t prime. So as I said the last time, if we think the monomial MIT is a monomial that sits here in this extreme of the edge, then I have the variable xj appears here if and only if the variable xi appears here. If you move one step, you have this relation on the variables. Axiom 4.
For axiom 2, should that be xj divides it? Because there's only there's no I, only j.
No, this is for all I.
Oh, for all I.
Yes.
And 3 is only for the I and j that are involved.
Yes, exactly. In axiom 4, we have 4 vertices. T1, T2, T3, T4, where the labels alternate. So we have I, J, I. So So I have this condition that in the last lecture I wrote 3 cases, but I want to give you the shortest way of expressing this axiom. This mi t3 divided by mi t4 is equal to mi t2 divided by mi t1, where we substitute in this expression xj with m0 over xj, where m0 is the sum of the 2 monomials that appear here, so it's mj t2 plus mj t3 computed at xi equal 0. So this is actually the same thing as what I wrote the last lecture. Remember that xi cannot appear in both these monomials by axiom 2. So actually, at the end, I have only one of these 2 monomials depending on the fact that xi divides mjt3 or mjt2 and so on.
No, sorry, no, I'm sorry, I don't understand. M0.
So this is a sum of 2 monomials,
Yes.
and you put
No.
xi equals 0.
Okay, thank you. No, I understand. Okay. No, it's clear.
So you delete the monomial where xi appears, if it appears somewhere.
No, okay, chiaro.
If it doesn't appear in these 2 monomials, then xj cannot appear in these 2 by axiom 3, and so the substitution is empty. So in any case, it's a monomial substitution. So the axiom 4, I would say that it allows to determine all exponents of the variables in all monomials MIT if we know the 2n monomials say associated to the n edges emanating from a given vertex. Let me explain this better. So if we fix a vertex T, then there are n edges emanating from T, and on these n edges there are 2n monomials. Okay. If we know these 2n monomials, then we know all the exponents d1, dn appearing in all monomials MIT, for all I and all t. Maybe we can justify this. This is an easy induction. So assume know all monomials associated to edges at distance.
If you do induction, don't you want to start with the pace 0, I mean the step 0?
Yes,
No. Because
Yes,
for me,
I will just wrote the induction hypothesis. The case k equals 0 is just the fact that we know these two n monomials. So let me write this definition. Distance.
in fact, the step 0 is already a problem for me. Right.
So we have t here. Then I have say n equal to 3 in this case. So I need a concept of distance of an edge from t.
No, but this is clear.
Okay, this is clear. These edges are at distance 0, these are at distance 1, this is distance 2, and so on. Okay. So, the two n monomials associated to the edges at distance 0 are known by hypothesis.
Wait.
This is the hypothesis. If we know the two n monomials, in this case the 6 monomials associated to these three edges,
Okay.
then we can determine all the
I was
exponents of
thinking
the n
the
monomials.
first step was n equal 1. Okay. Because for me it's not clear in okay, for n equals for k equals 0 fine. But for k equal 1, how? Because
Then we can do the induction
Yeah.
step.
I know, but like it's you're doing for generic k now or for
Yes.
okay.
But you can read this generic k with k equal 1.
I know,
it's
but
gonna be
you
the
don't
same.
see it.
Okay. So, assuming you have this edge labeled by j at distance k. Distance k plus 1. Distance k. So attached to this edge there is an edge at distance k. Okay. I can write it on the left. And this will be labeled by some I. This is the distance k. Then attached to this edge, to this vertex, there is another edge labeled by j. And what is the distance of this edge from t? It is at most k. Because this vertex was a distance k from the vertex t. So this edge also, it might be a distance k minus 1 or k, depending on where it is. So maybe we can
No, okay.
we can look at this example. If we start from this, a distance k plus 1, then we have this at distance k, and then we may have either this at distance k minus 1 or this at distance k. Okay. So in any case, this is distance smaller or equal than k. And so by hypothesis, we know the exponents of the monomials associated to these edges, and then we can apply axiom 4. We call this T1, T2, T3, T4. And by axiom 4 we have that n J T 3 and J T 4 is equal to M J T 2 and J T 1 with this substitution. M0 over xj, where M0 is the sum of the monomials associated to this edge. So actually we know all the exponents appear in this expression.
Shouldn't it be xi there?
This is
This is mj. These are all mj's, and then there is an xi, right?
MJ, which is xi.
Just from like.
Oh yes, because I exchanged the roles of I and J.
Yeah.
Yes, yes. So, thanks. So in any case, we know all the exponents of the variables appearing here, here, and here. And so we know the exponents appear in this quotient of monomials. And since these are monomials, if we know these exponents, if they are positive, they come from the monomial MJT3, and if they are negative, they come from MJT4, because these two are relatively prime.
Ah, they're relatively prime, that's the point.
Okay. So if in this expression we have x1 minus 2, x2, 3, x3, this some coefficient, then MJT3 is x2 to the 3, x3, and MJT4 is x1 to the 2. Of course, we cannot say anything about the coefficients at this point. We know just the quotient of the coefficient appearing in these two monomials. And this leads to the concept of normalized cluster algebras where all coefficients are equal to 1. In that case, everything is determined by the 2n monomials associated to edges emanating from a given vertex. Okay. So we are very close to the definition of cluster algebra. I need one observation. Since P is torsion free, then the group ring ZP has no zero divisor. They don't say anything about this. So I started trying proving this, and I got into trouble because I didn't assume that P is abelian. So I don't know if it is true, if P is not abelian. So I didn't succeed in proving this if P is not abelian. Maybe not abelian. Scusa. But if P is abelian, then it's easier. So let's see, if, let me say a few words about the proof of this statement. So if P is finitely generated, then it is clear. Because P, in this case, is Z to the n, it doesn't matter to Z to the n. And Zp is a polynomial ring in x1 to plus minus 1 xn to plus or minus 4. And so this clearly has a non-zero divisor. Okay? But if, in general, we can reduce to this case, because if we take two elements, A, B, in Zp, then we have that A is, call them X and Y. This AI, Pi, and B is Pi, where the Pi's are elements of P and AI and Bi are integers. With AI, Bi, integers, and so okay. This is just the definition of the group ring. So if we call P prime the subgroup generated by, this is a finite sum. And maybe some of these coefficients are 0. But then if you consider the subgroup generated by this P1 Pn, then this is a finitely generated abelian group with no torsion. So this is isomorphic to Zn, and we are in the case of a group, of a finitely generated group. And actually A and B belong to Z P prime. And so A, B is not 0 if A or B are not 0. Is it clear? So there is this small argument if P is abelian, but I don't know the result if you don't have this. Anyway, why do we care about this structure of integral domain in ZP? Is that we can consider the quotient ring of let's see. Yes, so we take a vertex Tn, Tn, and we define the field Ft as this is the quotient field of Zp in the variables x1, t, x. These are just indeterminate, but I write x1, t, xn, t to express the fact that they depends on t. So this is just the quotient of polynomials in this and variables with coefficients in Zp. And we can do this because this is an integral domain. Okay. Now, if we have two adjacent vertices, T prime with an edge labeled by I, We sometimes write also a further index p, which is the sum of the two monomials. P, in this case, is MIT plus MIT.
You write it there.
Yes, just a convention.
Okay.
Right, we define a map RTP prime from FT to FT prime. And we define it using the relation that we have seen at the beginning, in the last lecture, that we want to be satisfied. We didn't say anything about the relations here, so this is the point where we introduce the relations given by the exchange pattern N. So what is this map? This is I, so xjt equals to xj prime. This remains unchanged. And xit equals to p in the variables xt prime divided by xi prime.
Sorry,
Yes.
so j, is any j different from I?
Yes.
It must be.
It's, I. Yes. And the variable xit goes to this polynomial divided by xit prime. Remember, the relation was that the product of these two
What
was
is pxt? What is it?
p is this polynomial, which is the sum of the two monomials. So
It's the xt that I'm confused.
xt are the variables x1t, x2t, xnt. This is a capital capital xt. X1t.
Ah, okay.
xnt.
No, okay, I understand.
And observe that since p by definition doesn't depend on xi, sorry, we can compute this polynomial in xt prime or in xt is the same thing, because all the other variables are the same.
Repeat what did you say?
I say, since p doesn't depend on xi, if we compute p in the variables xt prime or xt, it is the same, because all the other n-1 variables are the same. By this. This is not a polynomial in xi.
By
No,
axiom
capisco.
1.
By axiom 1, yes.
Write the equality, then I try to.
The
So
quantity
this
is
is
the
the same.
I can write here p of x t divided by xi. So of course, if I want an element of ft prime, I have to write it in this way. But after this assumption,
Qua cioè non ho capito. Cioè sarà stamattina, but I don't understand. Don't understand what you're talking about. This tragic.
so it's not precise at this point, because I still I haven't identified these elements yet. So for the moment we live in two different fields.
fact,
So this element here is not here.
Yes, in
But-
fact, how can you say it's equal if it says no?
Yes.
No,
But then once that we identify this variable with this variable,
no,
this is what we are going to do now.
ma in algebra writing equality means equality.
Yes. Mod some identification that we are going to do.
We are going to, we have not
Yeah,
done
but if you
yet.
remember, in the last lecture we didn't say there is a map that send xjt to xjt prime. We said xjt is equal to xjt prime.
Did we?
So that's what we are going to do now.
Oh no, where did we say this? We
At the
said
very
it,
beginning.
okay?
This is
Yes.
what we want.
Yes, okay. It's a problem in algebra when congruences are mixed with equalities, at
Yes.
least for me.
Yes. So you can just erase this and look at this.
No,
No, I mean, this is not correct at this point. So maybe.
no, I understand what you're saying,
Yeah.
but
For the moment.
it's, no, I tell you what disturbs
Yes.
me. We are in the free situation, which is always that you do, no? When you have to write things, you go into the free. ZP, X1, Xn, right?
Yes.
Evidently, when you're in the quotient field, you have not imposed yet all the conditions that you have.
No.
You're going to, right?
Yes.
And this
Ft
one-
is just the quotient field of polynomials, rational functions with no relations. Ft. Okay.
So when you go, okay, no, I see, okay. Then you will impose the condition. You have not defined yet the cluster, right? The
No,
cluster.
but I will define it in the next
Okay.
flat.
Okay. No.
There is one further thing to say on this map, that is that it is ZP linear, because I didn't say where the coefficients go. So ZP linear, and it is extended to an algebra morphism. So I define it on the generators, and it is ZP linear. Well, now these are fields, and this is actually an isomorphism of fields. Let's see. R T prime is an isomorphism. And this is clear. I mean, this is a morphism of field is necessarily an isomorphism. Since it is surjective and injective.
Yes, because you are reaching all the generators. That's the argument.
Yes.
Because you reach xit minus 1 and then you.
It is surjective because I obtain all the generators in this field, xj t prime, and then xi t prime is obtained using
Yes,
this.
because you know that P does not contain xi. That's the key, right?
Yes.
Otherwise, okay.
Yes. Marta?
See, that's the next one. It does not contain X.
Yes. So we can use this map to identify the two fields Ft and Ft prime. And so all Ft, St varies in the tree. So we can identify all fields Ft with a unique field F, where all variables x, I, t live.
No, I have a question. So, Ft is a quotient field of this integral domain, right? So it's a question based on the fact that I don't remember. So this x1t, xnt, right?
Yes.
Ah,
These are algebraically independent variables.
the number n does
Polynomial.
not. The number n does not depend on t.
No.
Okay. So for each t, there is this integral domain, right? Which is the same for all.
Yeah,
So the fields are all the same. Why do we need this? We need this for some other reason. I mean,
the
the
fields
fact.
are the same, but I don't want the trivial isomorphism.
Right, that's because
I
you.
want this isomorphism.
No, I'm saying evidently the fact that we didn't need this thing to know the fields are the same. Evidently you want to keep track on how you reach a certain t prime through a certain path. And it's a tree, so there is only one path.
Yes.
This is what you're going to say, right?
Yes.
Great.
Yes.
In order to do this, shouldn't we have that RT prime t is the inverse of RT t prime?
Yes. Yes. And it's,
As otherwise, I don't know.
you're right, and this is true. Yes, I didn't say that. You're right.
Mm.
Yes.
Okay. I'm not fine again.
And this is trivial in this case, so maybe that's why I didn't say this. Yes, it's trivial because P doesn't depend on xj.
Mm.
And so when you write xi t prime, you just have to multiply this equality by xi t prime divided by xi t. It's trivial.
Mm.
So when you say all variables xit live, you just pick a particular edge I to be your reference, and then you
Right.
follow.
Yeah, that's what we can do, but
Okay.
here I consider all variables of all vertices.
Okay.
For any vertex of t, you consider the variable xit, and this is an element of this field.
Okay.
And some of them are equal.
Some of them are equal, of course. Yes. Yes, it may also happen that they are finite in number. I mean, this class of variables, they might be finite, as in the case of the Grassmann. In this form, they seem to be infinitely many, but many of them may coincide. So now we consider A. This is any subring of F containing not of F, containing 1 and all coefficients p I t. I equal to n and t. Definition.
Finally the cluster.
After 2 weeks.
Ma che 2 weeks?
Well, no, after 3 months. 3 months.
Right.
Yes, 3.5.
So, notice in this way, A, the index A, which is a subring of ZP containing all these elements, and consider it as a function of the exchange pattern. So the set of all monomials satisfying
So sorry for
Yes.
P abelian,
PID are the coefficients
the
of
coefficient
the
of
monomials,
monomials.
Okay.
which are elements of the group P.
He even says that we can consider them equal to 1 for normalized clusters.
Yes.
Right? So this is
Forget.
what. Forget about the P.
Yes. The AAM is subalgebra of F containing generated over A by all cluster variables xi So we first have defined this field, which contains all cluster variables. And then we consider the subalgebra generated by this cluster of variables over this subring, which must contain these elements because we need them to perform the relations among the cluster variables. Okay?
Okay, so this. I have a question.
Yes.
Because then I see there is something I don't really understand, and this is the same thing as the question I asked before. So F is unique, right? F is isomorphic to each of these F theories bigger than those. This I
It's
don't.
isomorphic to each of these.
To each of them.
Yes.
So
any element.
So it's integral domain, for example.
The algebra, yes.
No, F. F is
It's a field.
no, is the quotient field of this integral domain, right?
Yes.
Where is M in this picture?
M is in the relation among the cluster variables.
No, but where do you see M?
I mean, if you
I don't understand.
F is a quotient field of polynomials in the variables x1t, xnt for a
Okay.
fixed t.
For a fixed t, yes.
And if you consider another cluster variable, xit prime, this can be expressed as a quotient of two polynomials in the variables x1t, xnt. And to do this, you need the exchange
No,
pattern.
this definition is very obscure. I don't understand a word of it, really not a word. Because F is a quotient field of integral domain. Where is M? I don't see it in this F.
Yes. So,
As you know, where is the trace of all, where is the tree? Where is Tn in this
You
definition?
have all the
Yes.
variables, so you don't just.
Then F is not unique. F is not unique.
yes, it is.
I mean, it's not.
It is unique.
F, you can see F as the ft for something, for anything.